Where the fuck am I at? I'm at power. So.
Oh,
yeah.
okay. You're studying it on your own right now, right?
Yeah, I was on my own.
Oh, okay. Oh, that's cool. Because what edition do you have your textbook?
Are we talking about the same textbook?
For FE, the 2019 edition.
No, I don't think we have the same textbook.
Oh,
Let me
okay.
see. I'll post a picture.
Hold on. Let me allow screen sharing. There.
Wait, where is it? Where are you sharing?
I allowed screen sharing, so you can show me the picture.
Oh, no, it's the physical copy.
Yeah, I have the physical copy.
How do I see? Hold on. Share. You see me?
No,
This is
I
the one
can't.
I'm talking about. Nope. Nope.
Study for. I can't see because of your virtual background.
Hold on, dude.
Study guide. Damn it, the virtual background.
Okay, there.
Study
That's
guide
it?
for Study guide for fundamentals of engineering. Oh shit! Nice.
Yeah, it has like 500 plus questions.
Oh wow.
I think I'm at like more than halfway through already, so I don't know.
Oh okay.
Yeah.
Okay, because if nobody's gonna show up, we can start at power.
Hmm?
So I'm gonna go with the first problem right here, and then
Do we have the same book?
no, let me share my screen so I could show you. No, actually, let me turn the camera on. Why did I do screen share? This one,
Okay, cool.
the 2019 edition. Actually, Kevin in Tau Beta Pi bought this and sent it to me. So we'll probably do some problems in this book right here, and then up until 8 o'clock.
Okay. Oh, bear in mind that they changed the content for FE exam this summer. So
Oh yeah, July 1st,
yeah.
right?
Mm-hmm.
According to
Yeah.
the NCEES website.
Yeah.
Yeah. All right. So shall I get started?
Sure.
Okay. We'll
Wait, how are
start.
we gonna go about this?
So what I'm gonna do is like for every problem we do, I'm gonna transition to the. We're gonna go to the whiteboard when I screen share, so that way I can
Okay.
like write the problem out in text, and then I can even draw it out.
Okay. Cool.
Let's see.
Okay. Why don't you guys do it on Discord? Isn't it easier?
I did Zoom because what was it? Because it has like a lot of the functions at once, like recording and also the whiteboard.
Mm-hmm. Mm-hmm.
So the source is right here,
Okay.
and then
Oh shit! Let me pull out the handbook real quick.
okay.
Can't do anything without it. Is this the newest version for the handbook?
The 2019 version.
No. The reference handbook from Discord.
from Discord.
Yeah.
The one that I got was for the one that I have is from version 9.
Version 9.
Yeah, I think it was like 2016, 2019. I had to get it for what was it? EE400D.
Oh, the one I'm using right now is version 10, 10.0.1.
Oh, okay.
So, yeah. Do you want to get it? It's on
Uh,
Discord.
it's on Discord.
Yeah.
Yeah.
It's under FE Mechanical.
Okay. So, okay. So it's about time I use the touchpad now. Okay. So right here is your voltage source,
Okay.
and then this is node A, B, and C. So the inductor is going to be J10 with an impedance of J10, and then resistor will be 15 ohms.
Oh, shit.
Whoa, what's wrong? Okay. So now the question is asking us, oh, shoot, I forgot to write that. But it's asking us, what is the most nearly the RMS magnitude of the line current?
RMS magnitude of the what?
Of the line current. It's asking you to find what the line current is
Line
for,
current.
yeah.
Line current, line current. I am super bad with power stuff, so
So remember, this is a delta load. So the only time, shoot, I took 350 last semester. What is wrong with me?
with Woody,
Yeah, I did not like Woody.
dude, he's better than Slayman.
I think, no, what happened was this. He kind of turned into an asshole, like right after the COVID hit.
Oh shit.
So this is the impedance right here, and it's going to be represented as this is the phase impedance. So when you get the total phase impedance, we're gonna have to use a Pythagorean theorem for this. Let's see. And then plug that into your calculator. You should get 225 plus 100. Square root that. You should get roughly 18 for you should get roughly 18 ohms for each element for total impedance per line. So remember how we said that the RMS voltage is 120?
Yeah.
So that means from A to B it's 120. From A to C, B to C, it's 120. So now we got to figure out what the phase current is using Ohm's law. So the phase current would be roughly 6.67 amps. And then we have to figure out what the line current is in delta. Do you remember your delta? And do you remember your delta or Y line or phase current, current and voltage relationships?
Nope.
Well, in delta, the line to line voltage is going to equal the phase voltage, but the line current is going to be times square root of 3 of the phase current. So this is the equation we got to use. And similarly for Y, it's VLL is going to equal square root of 3 of the voltage phase, and then ILL is going to equal IP. So we have to use this equation right here to figure out the line-to-line current in a delta load. And then punch that into your calculator, you should get about 11.5 amps. Oh shoot, I forgot to write the choices down. So choice A is going to be 4.8, B is 8.5, C is 11.5, and D is 12.
Answer C then.
Yep.
Hold on, give me a minute. I'm trying to digest this.
Okay. Let me know when you're ready.
Yeah, dude. Okay, I'm ready, dude.
Okay. So same thing as before. I'm gonna type the problem out, and then we're going to then I'm gonna write the choices out. So let's see. Let's see. Okay, so options. Okay. So a 240 volt at a 0 degree source supplies a balanced three-phase load in a delta configuration. The line current is 3 amps at 45 degrees. What is most nearly the magnitude of the complex power measured across the load?
Complex power is S, right? Is it?
Yes.
Okay.
Represented by real power.
And wait.
No, sorry. Complex power is well, no. Apparent power is S. Then you have real power, and then plus J, complex power.
Okay.
So what
Oh
you'll
yeah.
note, so what you'll notice in the delta configuration is that. So remember previously when I wrote down like the delta and the Y.
No, dude. Complex power is S. Reactive power is Q, and real power is P.
Wait, what'd you say Q was?
Q is reactive power, and then the two combined will be complex power.
Uh, so in a delta configuration, if you remember, um, the what's in the chat here?
Oh, I just put the formula out there.
Oh, okay.
Yeah.
Yeah, exactly. So what I wrote previously was that the line to line voltage in a delta configuration is the same as the phase voltage. So we only need to worry about the 240.
Is it Y configuration? Uh, delta configuration. Okay. So the line voltage is the same as phase voltage, was it?
Yeah.
Okay, yeah, I see it.
So as the based on the equation you wrote in the chat, it is yes, S is equal to V times V times I. But remember too, in a delta configuration though, you have to times everything. You have to, what was it? Line to line current is going to equal square root of 3 times the,
Phase current.
yeah. So you have to times everything by square root of 3. So then you get square root of 3 times 240 times 3. We only need to worry about the magnitudes. So when you plug it in, you're going to get roughly 1247 VA, close enough to option C.
Okay.
You ready for the?
Is the solution C?
Yep.
Okay, cool.
You ready for the next one?
Yeah.
Alrighty. Let's see.
I think I had one of the workshop for FE last semester, and they said if you don't have enough time, just mark everything C.
I have a feeling like most of these people that write these tests or whatever, they're not even like. It's like they deliberately make a gag out of like writing like A or B or C.
Yeah.
So you have a balanced three-phase delta-connected system with three identical phase impedances. The line-to-line voltage is 240 volts, and the line current is 41 amps. Wait. Yeah, 240 volts, and the line current is 41 amps. And most nearly the magnitudes of the phase voltage and phase current in the system are A, 138 volts and 11.8 amps, B, 138 volts and 23.7 amps, C, 240 volts and 11.8 amps, or D, 240 volts and 23.7 amps. So this one, it's literally just driving what we know from a delta configuration for line-to-line or phase voltage and current.
Yeah. So its answer is D.
Is what?
Is D, I think.
Yes, actually, it is D. Because if you divide 41 by square root of 3, you get 23.7. So, yeah, option D. Nice. Okie dokie. Now it looks like we're going to move into the Y system.
Okay.
So, balanced three-phase Y connected. Okay, so you have a balanced Y connected. So let me draw this out. Okay, so you have a balanced three-phase Y-connected low system with three equivalent phase impedances. Most nearly the equivalent delta-connected phase impedances are 40 minus J30, 40 plus J30, 120 minus J90, or 120 plus J90. So, let's see. You got 40. Okay. So now we need to figure out, based on a Y system, what the impedances are. And we have to figure out what the equivalent delta connected phase impedances are. So we know that the phase right here for each, the impedances for each Y phase are 40 minus J30. So now there's one key equation that determines the delta impedance equivalent.
trying to find it right now.
Okay.
Oh my god.
So the key equation that we have to be concerned about is z delta is going to equal 3 times zy.
Dude, where do you find that?
I have it. I have the book right in front of me.
Oh shit, yeah, I see it. I see it. Oops.
So if you plug this entire expression into zy right here, you're going to get z delta is going to equal 120 minus j 90 ohms.
Okay.
So our option is once again C. C, C, C. Alrighty, so next problem, number 5. Balanced 3-phase Y-connected system has 3 identical phase impedances.
Dude, what would you do if the impedances are not identical?
If the system, wait, if the impedances aren't equivalent,
Aren't identical.
they have to be, otherwise the system wouldn't work.
Alright. Parent power.
Okay, so we have a balanced 3-phase Y-connected system with 3 identical impedances. Line-to-line voltage is 240. The line-to-neutral current is 41 amps.
Mm-hmm.
And the power factor is 0.8 leading. Most nearly the total apparent power in the system is as follows. What do you remember about the power factor?
Nope, not much.
Okay, so okay. So power factor is gonna equal cosine theta p, which is 0.8, but also it equals p over s. But we're not gonna dive into that yet because we don't even know what our complex power is. So we just need to do arc cosine on 0.8 to figure out what the angle is.
Mm-hmm.
So our power angle is going to be roughly about. So remember, do you know what lagging and leading are?
No, not really.
Okay, so if it's leading, that means the angle is negative. But if it's but if it's lagging, that means it's a positive angle.
Wait, leading is negative and then lagging is positive?
Yeah.
Okay.
So if you do So if you do cosine 0.8, it's going to give you about negative 36.87 degrees. So now we have to take into consideration the phase voltage. Oh, almost forgot. Since this is a Y connection, that means the line-to-line voltage and the phase current. Sorry, line-to-line current and the phase current are the same thing, but the line-to-line voltage is going to equal square root of 3 times the phase voltage. Wait, hold on. Did I do that right?
I think it's line to neutral. It's not line to line, right?
Yeah. Okay, so we have to take into consideration the, we have to use this equation again. But this is a three-phase system, so we have to times everything by 3. Ah. So we've already got the 3 in here for line voltage. So if you substitute it in, you're just going to do square root of 3 VLL times ILL. Because, what was it? If you look at the mathematics right here, it's essentially square root of 3 times... Wait, hold on. Phase voltage. I can't think today. I can't think today. I don't know what's wrong with me. But we have to also consider the angle, because we have a complex power here, right? And also the power angle to consider.
Uh-huh. Dude, shit. How do I send the equation to you?
What equation do you want to send to me?
It's the line-to-line voltage to phase voltage.
Oh, you can type it in the chat, and I can read it.
Can I put it on Discord?
Okay.
Yeah.
Let me take a look at it then.
Shit. How can I paste? Jeez. Oh my god. Yeah, I can't do it. I'll just type it out.
Okay.
Let me see. So, so it's like that.
For a three-phase.
VAN equals to VP. And then VBN equals to VP. Negative 20 degrees. VCN equals to VP. And then the corresponding line-to-line voltages is VEB goes to square root of 3 EP and so on. You know where to find that, right?
Yeah. Almost forgot. Since we had like the cosine and the plus j sine power angle here, we can essentially write this in phasor notation.
Yeah.
So essentially you get line to line is 240, and then ILL is 41.
ILL. Dude, the question says line to neutral, so I'm not sure if it applies there.
Then we just have to multiply it out to figure out what our complex power is, and from there, almost forgot. There's another crucial angle. There's another crucial equation we have to consider. The angle of the current minus the angle of the voltage. I think that's right. Let's see, phase, power, angle. What was it? Is it current minus voltage?
I'm trying to find it in the handbook.
Okay. Okay, let me see. 36.87. There's no voltage angle, I don't think. Oh yeah, it is. Okay, yeah, there's no voltage angle, so we don't even need to, we could just equate these two essentially.
What
Okay,
is phase theta I? What's that?
that's the angle of the current, because this is AC current, AC voltage.
Okay.
So that equation is what you use if you get, like, say, the angle of your current or the angle of your voltage. You can figure out the angle of your power, because current generally leads the voltage. punch that in the calculator. Okay. So we're going to get roughly 17 at negative 36.87 degrees, which we can represent with, so if we're going to get our real and apparent power, we're going to times that magnitude by cosine of this and sine of this. Which we can use with arc sine and arc cosine. So
I think
this
I
is
got
the
C.
so this is the yeah, this is the approximate answer I got too. So the closest we get is C. What's with all the C's lately?
Dude,
All
can
right.
you go back to the? Oh, did you delete it?
Yeah, I already deleted it. Sorry, dude.
Ah, shit.
So, oh, don't worry about this. If it I have this recorded right now, so I'll upload this on YouTube so you can take a look at it again.
Because I was wondering, right? The formula that you wrote down,
Yeah.
it's for line currents, but in the question it stated that it's lines of neutral. So how does that? How are those related?
Because you essentially have to do a conversion in the Y configuration from phase to line. Because remember, phase current and phase and line to line voltage. Sorry. Line to line current and phase current are the same, but for voltage, it's not. So you have to times phase by the phase voltage by a factor of square root of 3.
Okay. Now what I'm saying is lines to line current the same as lines to neutral current?
Let me see. Number 5, line to neutral current. Yes. All the currents have to be the same.
Okay, cool.
So we've got like a couple more problems. They'll probably be a little bit shorter. So ah Okay, so we got three identical loads of 4 minus J3 ohms and a delta connected three-phase system. The line-to-line voltage is 120, and then we have to figure out what the apparent power is in polar form. Ah. So given that this is a three-phase system, you know how we do like 3 times VLL times ILL?
Yeah.
But for to find ILL, we could also do this. So essentially, by using this substitution, we already have everything we need: the line-to-line voltages, the and the impedances.
Hmm.
So we could do 120 squared divided by 4 minus J3. We're going to need to convert this to polar form as well, and this will require some Pythagorean theorem and using a little bit of trig. That magnitude is 5, and that's going to be roughly, let's see, 4, -3.
Hey Eric, what kind of calculator do you use?
What kind of calculator?
Yeah.
Actually, right now I'm just using my computer and my phone.
Dude, what?
Cause what was it? I'm behind the computer all day, so I might as well, right?
Okay, dude. Um, so one of my friend told me he took the exam last month and he passed it. This
Uh-huh.
is the model that he used, and this works with complex numbers, so it's
Oh,
gonna
okay.
save you a lot of time.
Oh yeah, I think I'll see. I think I have a calculator like that. I just need to find it.
Yes. Yeah. Should check it with the website too if you want to make sure.
Yeah. So given we so if you remember how to like do use phasors and polar notation, you're gonna get a final answer of 8640 angle 36.87 degrees.
Yeah, I got that one.
So that should be,
B, right?
yeah. Wait, no, no, not B, because that's 280 to 880.
Wait, what? Oh shit, I forgot that. Wait. Oh yeah, yeah, you're right. Sorry, my bad.
Yeah.
I used the wrong formula.
Mm-hmm.
Okay, cool. I'm ready.
Alrighty. So we got the last problem in this chapter right here. So, Oh, oops. What was I thinking?
Dude, what does CA stand for?
Not California, just like the CA phase.
Oh, I've never seen this type of question before. This is interesting.
Okay. So the A phase of a balanced three-phase positive sequence system is taken as the reference. The line-to-line voltage is 277 volts, and the magnitude and phase angle of the CA line-to-line phase voltage is most nearly 277 volts or 480 volts at either 90 or positive 150 degrees.
I'm not sure how to approach this, to be honest.
Let me see. I'm going to do a little number crunching to kind of remember where I'm at. Oh, okay, okay. Okay, I know where this is headed. So in a positive sequence, look at the options we got here. We've got 150 and we've got negative 90, right?
Yeah.
So in a positive sequence, we have to assume that our angle starts off at 30, and then you add 120. Remember that equation you sent earlier about the angles?
The lines to neutral voltages?
Yeah,
Okay.
adding every 120 degrees. So in the positive sequence, so remember, it's going from C to A being the reference. So that means so when it goes from C to A, that means it's going to go all the way to either one of these options, negative 90 or 150. So when it goes from phase C to phase A, that means A, B, C, and then back to A. It's going to go, so if it's 30, it's going to go 150 and then 270. So more likely, we're going to have to end with 150 here, 150 degrees. And then now it's telling us that the line-to-line voltage is 277 volts.
Mm-hmm.
But this is what I meant by I was doing a little number crunching. I divided 277 by square root of 3. It's going to give you about 160, but there's no 160 here. So this tells us only one thing about 277. It's not the line. It's not the line-to-line voltage. It's the phase voltage.
Wait, what? uh,
And the fact the problem is telling us the magnitude and phase angle of the line-to-line phase voltage. Line-to-line phase voltage is kind of odd wording. Okay, but the fact that it's talking about line-to-line voltage, it sounds like it's going from phase to line-to-line.
hey, Eric.
Huh?
Okay. Do you see the list of formulas I sent earlier? The
Yeah.
corresponding line-to-line voltages?
Yeah.
So the latest one I had is the V A to B line-to-line phase voltage, right?
Yeah.
So the completed list is VC to A equals to square root VP 150. So that's the completed formula.
Yep.
I think that's the one we need for this question.
Indeed, it is. So if we do square root of 3 times 277, it's going to give you about 480 volts. So that's going to give us option D.
Yeah.
Alrighty. We finished the entire three-phase power chapter today.
Nice.
No problem. So next time we work together, so what was it? Out of curiosity, before we, what's your name? Hien?
Ian. It's like Ian with an H.
Okay. So Hien, which section do you want to do next? In which topic? Mathematics, probability, materials, electromagnetics, power, or electronics, or control systems?
Let me see. I want to work with the ones that I'm not too strong in. So
Okay.
give me a minute. Because I think math is okay, honestly.
Okay.
Do you want to do electromagnetics?
Okay. Yeah.
Have you done 360 yet?
Not yet.
Shit.
I'm supposed to though. The best option I got, according to some of my one of my classmates, is Chang, and well,
Oh crap.
people, but I'm not sure about him because, like, you know, of what happens at how he teaches in 310.
You had him for 310?
No, but I heard terrible things about his 310.
I had him for 310. It was rough.
I had Musavi.
Oh shit.
She's good, but she's tough.
Yeah, I don't know. I don't quite like her teaching, but I think she's a little better than Chin Chang.
Yeah. But yeah, we can do electromagnetics next time we do our session next Saturday.
Sure, dude. Wait, was that everything for power?
Just three-phase power. What's next
Okay.
is what would have been next was transmission lines.
That should be easy.
Okay.
Yeah, let's do electromagnetics next time.
Okay.
If you're down to it.
Alrighty.
So wait, so is the whole thing is gonna be like an hour every Saturday? Is that it?
Yeah.
Okay. All right. Thanks, dude. Appreciate it.
No problem, Ian. I'll see you next Saturday.
Wait, dude. Can you answer something?
Yeah.
Are they gonna do induction this semester?
Oh, you're interested in Tau Beta Pi?
Yeah.
Oh. Did you get the email from TBP?
I have been getting their email every semester, but wait, I don't think they sent out the email this semester yet, so I'm not too sure.
Oh, so you've been getting their emails?
Yeah, but
What?
I haven't been joining.
You didn't want to join them?
like last semester, no, last semester, I was in HKN, and then last semester the COVID thing, so
Oh, that's right. That's right.
yeah.
It did kind of mess with everyone's induction when COVID hit.
Uh-huh. So are they gonna do induction this semester? You know?
I'll ask. Well, I'm the shadow internal VP. I'll ask the VP internal or the president what's up.
Okay, cool.
Okay, but yeah, if you're still interested, I'll be sure to let them know as soon as possible.
Yeah.
Okay,
I should be able to get in. As in I should be able to get that email. I think my GPA is okay. It's not too
all
bad.
right, alrighty then.
All right, have a good
Um,
night, dude.
all right, you too, Hien.